Boom. Right, we are recording. So, hello YouTube for those who have just joined us. And this is now a bit more lecture on chapter 2. We'd finished off with that Monday lecture or Monday YouTube video talking about isotopes. And we talked about how some isotopes are actually radioactive, but that can be useful. Although radiation is dangerous, we can use small amounts of radiation to try and treat patients with cancer and sometimes detect cancers and other diseases. Isotopes, remember, are elements with atoms which have the same number of protons but different numbers of neutrons. So we get different mass numbers for atoms of the same element. But it's got to be the same atomic number, the same number of protons, or it's just a different element. Let's quickly check the chart. Yeah, lab can be stressful those first couple of days. It's so important to have the lab packet printed off. So important to at least take a peripheral read of it. And if there is a video available, watch the video. Okay, people, I'll still help you. I'm not going to refuse to help someone or refuse to answer a question, but you just feel a little bit less wound up if you've already seen a video on it. Okay, let me see where my pen is. Right. So taking a look at the periodic table again, briefly, we had talked about some of the columns, these groups, being given their own personal name. And we had also already mentioned that that very final column, that very final group, group 8 as it's known, the numbering does tend to vary a little bit, but normally when we talk about the groups and the number, we're commonly referring to this first column as group 1. Then we have group 2. And although some chemists include this transition block here, most people don't. So if we're talking about group 3, that's normally referring to that block there, starting with boron, then 4, 5, 6, 7, and then of course finally 8. If we include this middle block, then this becomes 13, 14, 15, 16, 17, 18. But certainly from my point of view, I just use the far left and far right blocks in terms of numbering. So group 8, that's our noble gases. Group 7 are the halogens. And we also give names to the first two columns. The alkali metals, that's excluding hydrogen, which of course isn't a metal. But all the other elements after hydrogen are alkali metals. And in group 2 are the earth metals, as are known. Middle block here is sometimes known as the transition metal block. Okay, and we usually talk about them separately because their chemistry is a little bit different. As we saw in chapter 1, we've got that main divide between metals and non-metals going through boron, the first of the metalloids, and therefore everything else to the right is a non-metal. And then we just include a hydrogen on that list. And almost everything else to the left is a metal, excluding germanium and antimony, the extra two metalloids. So the shape of the table is about chemical reactivity. And every time that Mendeleev found an element that was similar to hydrogen, he would start a new period, a new row. And so the elements in each column, each group as we know them, these are always elements which are similar in their chemical properties. So lithium is similar to sodium, which is similar to potassium, rubidium, etc. Just as fluorine is similar to chlorine, similar to bromine, iodine, etc. So if we take a closer look at some of the properties which are common for the different groups, the first group, group 1, the alkali metals, these are elements which, when they do ionize, which we'll talk about next week, they always have a charge of +1 every single time. When we add them to water, the reaction of an alkali metal with water is incredibly vigorous, quite explosive at times. That's not something you'd want to be standing next to and observe, not without some serious protection, like a blast shield. I have a very violent reaction with water, and it produces a strong base, what we call a hydroxide metal base. So react sodium with water, we produce something called sodium hydroxide. We react potassium with water, we produce potassium hydroxide. These are examples of bases and very strong bases. The reaction to produce them is always marked by producing a lot of heat energy and probably be very loud with crackling and popping. Hydrogen is produced as a side product. It's one of the reasons it makes it so potentially dangerous, because you've got this hot burning piece of metal in water, it's producing hydrogen, and that can cause that hydrogen to catch fire as it's being produced. The alkali metals are also metals that tend to be very soft. You can usually cut into them with a knife, they're that soft. And they also have relatively low melting temperatures compared to other metals. When I say low, I mean melting temperatures often less than 1,000 degrees Celsius. Well, iron, of course, has a very relatively high melting point. I can't remember the melting point for iron, but I think you're very much over 1,000 degrees. But because the furnace can be stoked very hot. So, and like any metal, it starts to become soft before it melts. So it's, oh, excuse me. Yes.
My show finished.
Your show finished. Okay. Go have fun, okay?
Now I can play with you.
Oh, but I'm working, sweetie. I'm doing work. Can I get you something else to watch, or can I get you a treat?
Give it to me.
Yeah, have you a treat. Okay. Can you sit with Robert and watch some Minecraft videos?
But I just
Okay. Right, give me a second, guys. The Teenage Mutant Ninja Turtle video finished. Drat, hang on. Right, sorry about that. That should buy me a bit of time while she works on a sucker. Okay. Excuse me. Right, so let's see. All right, so talking about the alkali metals, low melting points comparatively, like maybe like this 8 or 900 range rather than 1,000 or 2,000 degrees for the melting temperature. They're soft. They always ionize to a +1 charge. Very shiny. Group 2 elements, that's all metals, the earth metals as we call them. They're also soft. You can often cut into them. But an increasing number of those elements are starting to get much more harder and more difficult to cut through. they have relatively high melting temperatures, and they react with water as well to produce a base. But this time the reaction is much more gentle, although it will fizz and pop a little bit. As long as you had safety glasses on, you wouldn't be too concerned about standing next to one of these reactions. That would be fine. But the base produced this time tends to be a weak base. So while the alkali metals react violently and produce strong bases, the earth metals react much more mildly and produce weaker bases. We move over to group 7, the halogens. Those halogens are actually amongst the very few chemicals which have a natural colour to them. Bromine is a kind of off yellow colour normally. Sorry, not bromine, fluorine I should say is a kind of off yellow colour. Chlorine is green, bromine is blood red, and iodine has a kind of purple tinge to it. Very few elements actually have colour. You can certainly make chemical compounds that produce colour, but individual elements, it's rare to see colour. And most of the examples are the halogens. The halogens also like to react with group 1 alkali metals, and they produce these salts. So sodium reacting with chlorine to produce sodium chloride, or sodium reacting with bromine to produce sodium bromide. We'll talk more about these kinds of reactions and ionic salts in chapter 3 next week. Also interestingly, they're amongst a very small set of elements which are diatomic. The atoms like to pair up with one other atom of the same ilk to make a molecule. There's a couple of other elements which like to be diatomic. Let's see. Get my pen out. Okay, so as well as the halogens, hydrogen is also diatomic. Oxygen gas is also diatomic, as is nitrogen gas. But no other elements in their group are diatomic. So to have the entire group be diatomic, that's something we just see with the halogens, group 7. And looking at group 8, our last group, last element at the end of each row, each period, that's our noble gases. Noble gases are colourless gases, and they're also incredibly unreactive. It's almost impossible to get the noble gases to react in any way with any other chemical. There's a couple of exceptions in there. Krypton does do a couple of reactions, and as does, I think, argon. It's usually incredibly difficult, normally taking high temperature and high pressure to encourage that reaction. Certainly nothing particularly interesting happens with the noble gases. So they're unreactive. We sometimes describe them as being inert gases. So as we look at the periodic table, we see a couple of trends in the table, trends that we're going to think about in this chapter are the atom size and the atom electronegativity. Electronegativity is just a fancy way of describing how good the element is at attracting electrons towards itself. So electronegativity. Electronegativity. Scrawled in my terrible handwriting, of course, unfortunately. So how good are they at attracting electrons to themselves? So when it comes to the size of the atom, the size of the atoms as we look along the rows, these periods, so the periods are from left to right, and then the groups, are up and down. So for these periods each time, we find that the bigger atoms are on the left. So bigger atoms to the left and smaller atoms to the right. Once we've had some time to talk about subatomic particles like the electrons and how they stack, we can make sense of that trend. Just for the moment, lock into your mind, the atom size starts to shrink as we move to the right. We also see changes in atom size as we move up and down the table. The smaller atoms tend to be at the top, and the bigger atoms tend to be at the bottom. So the very smallest atoms are on the top right-hand side. That's our nonmetals. And the bigger elements and atoms tend to be to the left and to the bottom. That's the metals. So whenever you're comparing the size of a metal atom to the size of a non-metal atom, almost every single time, the metal will win. It will be the bigger of the two atoms. The other trend we talk about in this chapter is the ability to attract electrons, that electronegativity. We find as we're looking across the period from left to right and right to left, that electronegativity increases as we move to the right. So the atoms get better or stronger at attracting electrons as we move to the right, and they get weaker at attracting electrons as we move to the left. Looking up and down the periodic table, that attraction for electrons, the electronegativity, gets stronger as we move towards the top and gets weaker as we move towards the bottom. Again, following that divide between metals and non-metals. So although non-metal atoms tend to be smaller, they're actually better at attracting electrons. While the metals, being bigger, are actually worse or bad at attracting electrons. That's the two main trends we want to talk about in this chapter. And we'll be able to explain why these trends happen once we've looked at electron configurations. So let's give this a try. Let's see, give me a second. What time is it right now? 11:29. So let's use this as a 5-minute break. So if you want to grab a drink or take a bathroom break or something, let's do that now. I'll take 5 minutes and we'll try a couple of polling questions, but I have to just set that poll up.
Hey, Dr. E, I have a question.
Sure.
So I was, this is kind of weird, I guess, because I don't know, but I was looking at my schedule and it says hybrid next to it, but then it says that my like lab time is, hold on, I'll just take a picture of it. It said, so it says hybrid next to my like section or whatever, but then
Uh-huh.
it says Monday 2 to 4:50. So I guess that I missed that yesterday, but can I still just come today at 6 and then like next week start going 2 to 4:50?
So let's see.
I think I accidentally switched them.
Maddie, what's your last name?
Sanders? I know it's
Anders? Let me just check what section you're in, because lab on Tuesday, Thursday is section 2. Lab on Wednesday is section H1. Let me just log in and check.
yeah, on my schedule it says Chem 141-01 and then 1-hybrid.
All right, so it sounds like you're in section 1 and should have been with us on Monday. Let me check.
Oh, okay. Well, I can even though I wasn't there Monday, could I still come today at 6?
You can probably come today at 6 because seeing as we're splitting the class into 2 halves, that gives us room for a few more people, but only a few more.
Yeah, no, it
Let's
won't
see.
happen again. Sorry. I
That's all right. That's all right. We know we're trying to get it together, and the administration, without being too critical, hasn't really had it together
Yeah,
But
no.
we're all kind of trying to cope at this point. Let's see. Let me check. So we now suspect you're in section 1. I don't see you in section 1. Let's see. Section 2. Sorry, what's your last name again?
Well, my first name's Madison. It's probably not going to come up as Maddie. And then my last name is Sanders.
Oh,
S-A.
Sanders. I thought you said Anders there.
Oh, no.
Which made me
Sanders.
think you were part Norwegian.
No, I'm Italian. And it's weird because I don't have an Italian last name.
Aha. So, Madison, you are indeed in section 1. And so officially for lab, you meet on Mondays in the afternoon. Don't worry, there was a couple of people missing.
Okay.
So
All
I
right.
think we can fit you in tonight at 6 o'clock. That should be fine.
Cool. Thank you.
Let me see.
Sorry, this online stuff is just kind of different for me.
That's all right. Everybody's kind of um,
It was hard for me when I first started, and that was like a few years ago,
right.
Yeah.
and that was for
It's
summer school.
it's kind of it becomes hard for everybody because uh, I have to watch what I say here. Um, I normally only teach one hybrid class in the semester, and then they decided to switch all my classes to hybrid, which for me means, if you're talking about hybrid, that means that you meet on campus for lab and then you're online for lecture. And as you might remember in that first week, I had to change my plans because the college suddenly said, oh, no, 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 you're meeting your students on campus for lecture. Well, where's the hybrid part of it?
Right.
There's no real hybrid part of it, unless you're in H1 because they don't meet officially for lecture. So, yeah, they're being a bit weird.
So this might be another dumb question, but just to make sure we only meet for our labs, like for our section.
For section 1, you're just Monday afternoons, that is it.
Okay, cool. All right, sounds good.
Bear with me now, I'm just trying to get it there. So the poll questions. If I was really on the ball, I would remember that we were doing this and I already have it set up. So my bad today.
No, you're good.
Let's see. Aha, here we go. One sec, almost there. We did a poll yesterday and now I'm trying to find how to clear. Ah, there we go, clear. Right. Okay. Let me drag this across where people can see it. Let's go full screen. Here's some polling questions for us to quickly try. So if you just grab your phone, and let me give you the address for this. I can write this up. So on your phone or on your computer, just go to www.pollev.com/, and then it's, oh, in fact, there it is up there. James Elliott 471. Doesn't have to be capitals. I just have terrible handwriting. So www.pollev.com/James Elliott 471. And let me see, I have to, yep, it should be activated. You should see this right now. So which of the following elements is red in color? Is it argon, sodium, bromine, or zinc? Now you're not, this is not for credit. I just want to see how people are doing from the material that we've been talking about this morning and this week.
Hey, Dr. Elliott, I just have a quick question.
Sure.
So do you have to make an account?
And for this, I don't believe so. I don't think so.
Okay, 'cause I just don't see, it's showing that I have to like enter in an email and password.
Anybody else? Is anybody else having that problem?
No, but I know that you can download the app. I think Poll Everywhere is like a app you can download.
Okay, sweet. Thank you so much.
No problem.
Normally, I get a count of how many people have taken the poll. Where is my count? Is everybody getting the answer of bromine?
I didn't get it. I didn't put it in yet.
Don't worry about it. Don't overthink it. Just go with your gut. Completely anonymous. Just about putting in a response. What does your gut tell you right now? If you think it's something else, don't let the 100% for C affect you. Maybe 100% of people are wrong. Go with your gut. That's all I'm trying to get, a sense of the gut, your gut response. And it gives you an example of the kinds of things we should be thinking about. And it also lets me know how well the material is going for people at this moment. Somehow I'm supposed to see a count, and I don't understand why that's not there. Okay, I'll assume that everybody in unison thinks it's 100%. And for this one, you'd be right. We just talked about it about 15 minutes ago. Bromine has a blood red color because it's one of our halogens in group 7. Okay. Let's try another one. Whoops, still got that writing up there as well. Sorry about that. Okay. Now for this one, which of these elements is a strong base in water? Would it be neon, fluorine, calcium, or lithium? Again, do not worry about whether you're right or wrong. This is not for any credit, and it's not something which comes up in terms of any any revelation of identity. So calcium and lithium are two choices, although lithium certainly seems to be winning. Don't change your answer. I'd catch people doing that all the time, changing their answer. You could be in the minority which is getting it right. Thankfully, nobody seems to think it's neon, because that's one of the noble gases. It's unreactive, so we certainly wouldn't expect it to react and produce a strong base. Fluorine, nobody likes fluorine either. That's correct. It's a halogen. It doesn't produce bases in water. The correct answer is actually D, lithium. Group 1 metals, or alkali metals, are the ones which are reacting fiercely to produce strong bases. Group 2 metals like calcium also produce bases, but remember we said they were relatively weak bases. Okay. Interesting. Let's see. Let's go to our final question before we do a little bit more this morning. So let's see. Full screen. So which of these elements has the biggest atoms? Interesting. Silicon, magnesium, sulfur, or aluminium? Might help if we look at a periodic table as well. See, what was our options again? Yeah. Silicon, magnesium, sulfur, aluminium. So we have, let's see. Silicon, oh, why is my pen not working? So silicon, magnesium, aluminium. What was the last one?
Sulfur.
Sulfur. Okay, thank you. First thing to notice is that we're talking about elements in the same period, from left to right, period-free elements. So what was our trend? Do the elements get bigger the further to the left we move, or do they get bigger the further to the right we move? Good Lord.
Sorry, I had to yawn.
That's all right. Thought it was a bear attack for a second there.
Why would there be a bear in my room?
I don't know. Well, bears are sneaky. Have we seen the video? They're carrying nunchucks now.
The only bear I want in my room is a teddy bear or Winnie the Pooh.
Let's see. So is everybody responding here? Everybody? I can't see numbers, which is annoying. Oh well. So I imagine that most people have replied at this point. So yes, magnesium is the element with the biggest atoms from this list, because as we look at the periodic table, elements to the left, the further left we go, the bigger the atoms get. So magnesium would have the biggest of that list. Sodium would have even bigger atoms. Okay. Hopefully that just spiced things up a bit and made things a bit more fun. Let's see, I'll unactivate that. Take that down, and then we can forget about that. Right, next time I'll be a lot more organized and more ready for that. Okay, so that's some of the things we've been talking about today. Let's see, I want to just squeeze an extra 5 minutes. Well, I've got 5 minutes, I guess, and just quickly talk about electron configurations. We'll talk about them more on Friday for the next online lecture. Of course, for section 1, you'll actually be in class on campus for electron configurations, and later in the day I'll produce a video based on the material that I go over in class on Friday for people who want to watch from YouTube. So we're now thinking about those subatomic electrons outside of the nucleus. Those electrons arrange themselves into layers, almost like floors of an apartment building. You could almost imagine it as airplanes being stacked up around an airport if there was snow and ice shutting down the runways for an hour, because the planes probably can't go anywhere else, so they have to just start flying around, waiting. They can't go too high or too low or too far west, north, east, or south, because they could run into other planes which are just in a holding pattern and flying around the airport.
There was one plane who tried to take off when it snowed and it crashed. Most of the people on board died.
Yeah, that's what happens if you ignore the tower. So these planes have got their little pockets, or little zones of space that are allowed to fly around in until the weather clears up. But that's kind of like what's happening with the electrons outside of the nucleus. Oh, thank you, sweetie. That's very good. My daughter always makes sure she gives me her trash, like a now suckered out lollipop. So in these little fly zones for the electrons, and these little pockets of space are what we call orbitals. Just a fancy name for a pocket of space where we can find a maximum of 2 electrons. A little bit like maybe a landlord with having a rule of 2 people in any one bedroom living. So these orbitals are areas of space where we find electrons, 2 electrons at a time. And these orbitals, as we call them, these spaces, think of them as actual individual rooms in a building. These rooms often stack together to make apartments. Then the apartments combine together to make an entire apartment block, an entire building. So the simplest kind of apartment that we can describe is what we call the S subshell. And just like a studio apartment, it's the entire apartment, but it's also just one single room. And this is what we have with an S subshell. Just a single orbital making up that subshell. And it's got room for up to 2 electrons while staying away from the nucleus. So maybe the
It's like a
electrons
tiny
are up
planet.
here, or maybe they're down here, or somewhere around here. We don't know exactly where they are because the electrons are always on the move with kinetic energy. Just like over a course of several hours or a day, if you're quarantined in your apartment, you might move to different parts of the room depending on whether you're trying to watch TV or read something or do the dishes in your apartment. So with a 95% probability or better, they're somewhere in the space. Was there a question in there?
No. I was thinking like when you said it was like one room, it made me think of like when that time Dad and I were in a little cabin. It was only one room,
Right. So
except
it's
it was
just a single room, and that also describes the entire apartment. That's what we call the S subshell. It's made up of just one orbital, so we have a maximum occupancy of just 2 electrons. And quite often we'll just draw that as a box, a single box like the outline of a single room. Now, as we move further away from the nucleus, we start to see much more luxurious or larger subshells. Just like in a hotel, the best rooms tend to be on the top floors. So we also have what we call P subshells, and these are made up of 3 individual orbitals, like now with an apartment which contains 3 bedrooms. It's the same basic rule of just 2 electrons in each orbital, or 2 people per bedroom. But the shape of each of these orbitals is different from what we saw in the S subshell. Now each orbital looks like a propeller blade, either side of a nucleus. And so the first one is straight up and down on the y-axis. The second one goes from left to right on the x. And then the last one goes in and out of the page on the z-axis. Each one of these propeller blades can take a maximum of 2 electrons. So a p subshell can hold a maximum of 6 electrons with its 3 orbitals. Again, as we draw the orbitals, we just draw them as 1, 2, 3 boxes side by side. finally the D subshell, a little bit bigger, a little bit more roomy. It's actually made up of 5 orbitals. Just think of a kind of a balloon artist making different shapes
Balloon animal,
for
like
a
the
little
classic
kid
dog.
with the balloons. So the first orbital is, we are describing that space. One sec. Yes, baby.
Do you know?
Hmm.
I
Why don't you ask me in a minute? Let me finish this, okay? Come sit with me. Okay, gotta be quiet, okay? Gotta be quiet. Shh. So the first orbital is describing the space in between the X and Y axes. Second is turned, rotated at 90 degrees. And now we're talking about the space between the Y and Z axis. Third one is a space between the Z and the X. Fourth, shh, careful, shh, calm down, is along the X and Y axis. So not in between, but actually along the axis. And then the final one is along the Z axis. So think of it like these blown up balloons. And somewhere inside this balloon space is where the electrons are living. 2 electrons at a time. So it gives us a maximum of 10 electrons with these 5 orbitals.
You know they're definitely in there if you rub them on your head.
I know. So if we just take a quick look at how these subshells combine together. So the electrons basically align themselves into layers or shells, like floors of an apartment building. And with each floor of the apartment building, there's individual apartments and there's individual rooms in each apartment. Okay. Now, the order that they appear is always the same. So don't be overawed by this. What we're going to do on Friday is show how we can use the shape of the periodic table to make this all very simple and easy, okay? Right, any questions before we split up, guys?
No. Okay,
we're doing okay? Yeah, somebody's getting very impatient for lunch, I think. Okay.
Yeah, I don't know why, but I feel like I started thinking about the movie Unstoppable.
Uh-huh. Okay.
Probably because of like one of its cargo in the tank cars they were carrying a chemical called molten phenol, and I didn't really understand much about that.
Okay, guys. I guess we'll stop it there because I've got a cheeky monkey to deal with. Remember, text me at 364-5546 if you have any questions. I have office hours. And I'll talk to everybody on Friday morning on campus. Bye, guys. Stay safe. Wear your mask. Wash your hands. You want to say bye? Say bye-bye. Hey, say bye-bye. Say bye-bye. Bye-bye. Bye. Say, I'm a cheeky monkey.
Good enough.
Bye. Somebody's had too much sugar.